Okay? Now, it turns out that radioactivity is a first-order chemical equation. Now, technically, when we talk about chemical equations or chemical reactions, we're talking about things that transpire in the electron area. Okay? Electrons moving from one substance to another create ions, or shared between two atoms, which we call covalent bonds. Those are all electronically driven reactions, and those reactions are what we've been talking about up to this point. There is a section in Chem 2 dealing with reactivity or nuclear chemistry that we probably won't get to, which is a real shame, because it's an aspect of chemistry that is largely ignored and thought of as really difficult, and it's actually really simple. But the deal is this: the difference between nuclear chemistry and regular chemistry is that nuclear chemistry deals, as the name implies, with the nucleus, changes within the nucleus, which is kind of a strange thing for most people who've been studying chemistry up to this point, because everything has been electronically driven. Nuclear chemistry is nuclear driven, meaning particles within the nucleus can change, which is what makes them so crazy, how shall I use it, dangerous, because particles that get spit out are things like alpha particles, beta particles, gamma particles. These are all radioactive materials because you have a nucleus that is so unstable, it wants to kick out stuff to make it more stable. And so there's a tremendous amount of heat involved in these reactions compared to regular chemical equations or chemical reactions. The power plant we have in Cordova is a nuclear power plant. It runs on nuclear reactions, in which the particles being spit out are gamma particles, which are extremely dangerous, and neutrons, which are also kind of dangerous, especially but only in a creation of a chain reaction. Again, I don't want to get too heavily involved in this, but we have a power plant which I believe is important to our society as we're trying to get off of the carbon-based economy. These guys are going to be so helpful in getting us in that transition from carbon-based fuels to other fuels. Nuclear power is a very clean energy as long as it's done correctly. That's the big if. But we have this power plant here, and what we have there is this isotope, uranium-238. Now, uranium-238 is one of the most stable uranium isotopes there are. The nuclear bombs that we have dropped, one of them used uranium-235. Well, uranium-235 is incredibly unstable and creates a chain reaction quickly, so violently, that if you've ever seen pictures of the atomic bomb dropped on Hiroshima, that was the substance being used in that. Then the amount of heat being given off is, I would say, millions of times more heat than a reaction used to burn the fuel for your house. So, if for some reason, and this will, the odds of this ever happening is so exceedingly small, but if there were to be an explosion and pieces of uranium-238 go flying all over the place, the half-life for these things is 4.5 billion years, which means that it'll take 4.5 billion years for half of the material to become something else, which will most likely also be radioactive. So once that showers, we're in serious trouble. No one could ever live in this area again. This is why they also say that a dirty, they call it dirty nuclear bomb, is more dangerous than a regular nuclear bomb, in that if someone can steal the stuff and make a bomb out of it, it would render that entire area that's affected by it completely uninhabitable, probably for the rest of the duration of this Earth's lifespan. So they're very sensitive about the material getting in the hands of the wrong people, which is why they take so much precaution, which is why it's so expensive to run these plants. But in the long run, we're better off for it because they do an incredibly great job of making sure that nothing can be kidnapped or removed from the plant. So, but the deal is that it's all first order reactions. So the half-life, if it's 4.5 billion years, that means half the uranium-238 will turn into something else. And then that something else, which again I say is probably going to be radioactive as well, with its unstable nuclei, will then turn around and have a different half-life. And at some point, it could be an issue where maybe it becomes inhabitable if the Earth is around that long. In Chernobyl, in Russia, where they had the explosion over there, it killed everything around, and that in the general area of Chernobyl is still uninhabitable, although they're saying now that there's like 3 inches of dust over it, so it's covering the radioactivity, and there's like some creatures that who walk on the ground like deer and that kind of thing are not affected by it now, the new generation of deer that they have, but the ones that kind of burrow into it don't live. So, but that's all, the science of that is all based on first order half-life reactions, which is what we're talking about. So, let's take a look at how we come up with the formula for doing that. We have this first order equation that we've dealt with, and that is that the natural log of some substance at a particular moment in time, whatever that is equal to negative kT plus the natural log of the substance at the very beginning. Okay, so what I'm about to do now, you don't have to worry about knowing this. I'm just showing you where these things come from. I don't like teaching material where you say, oh, here's a formula, memorize it. No context whatsoever. And when you go to college or a university, whatever it is you go to, you're going to find your professors are going to show you this, and it will not benefit you now, but probably later on when you get much deeper knowledge of chemistry, and you're taking these college chemistry classes. It might be a good idea to understand how to do these as well, but not right now, not a biggie. Well, let's suppose that we want to find out concentration at the first half-life. Okay, so we'll call that T sub 1/2 instead of T. And so that's going to equal to negative K T sub 1/2 times the half-life plus the natural log of the original concentration. Okay, so we've got this right here, and this 1/2 should be not in front of it, but it should be right here. So I'm going to switch that over like so. Put the 1/2 there. Okay? So this becomes the natural log of 1/2 A sub 0 equals negative K T 1/2 plus the natural log of A sub 0. So now I'm going to subtract this and bring it over here, and this gives me the natural log of 1/2 A sub 0 minus the natural log of A sub 0 equals negative K T 1/2. Now, the reason why this becomes important is because when you subtract exponents, remember logarithm means exponents, so when you subtract exponents, you're actually dividing the two quantities that have the same base. In other words, this is an exponent of E, this is an exponent of E, and when you subtract the exponents, you divide the quantities that have that same base. So this becomes the natural log of 1/2 A sub 0 over A sub 0 equals negative K T1/2. Now, conveniently, these two cancel out. So that leaves us the natural log of 0.5 equals negative k T1/2. Now, what we're trying to do here, the whole point of this, is to come up with an equation in which we can calculate the half-life of a chemical equation based upon the value k that we figured out from its first order equation. All right? So, if you punch that in your calculator, you get negative 0.694 is equal to negative k T1/2. You also notice that we have a negative on both sides, so they both will become positive as we pretend like we're multiplying both sides by -1. Again, the whole point of this is to get T1/2 by itself. So we divide both sides by k. And you get T, so 1/2 equals 0.694 over k. And that is your equation for half-life that you can put into your chemistry toolbox.